morning, class. This is the second of three videos covering normal distributions. I heard from several of you, and I know that you have received the material I sent, which was reassuring. Okay, so the previous video, we looked at the standard normal distribution. Let me mention a couple things about it. So we denote the random variable of the standard normal distribution by the letter Z. That's traditional, and there are reasons for doing it. Okay, so it has the shape of a bell curve. I graphed it in class for you with the graphing calculator. Now the curve is bending up, and then it starts bending down, and then bending up again. So there's a point where it goes from concave up to concave down, and then there's a maximum point, and then another one where it goes from bending down to bending up. These are called points of inflection. This is a maximum value. It turns out that this number here is the number 1, and this is 0, of course, and this number is minus 1. And it's also true that the mean of the standard normal distribution is 0. It's easy to believe that. We use the Greek letter mu to denote the mean, and the standard deviation is 1. It's the distance from the maximum point to the point of inflection here, the horizontal distance. And the letter for that is lowercase sigma in the Greek alphabet. Okay, now the random variable for any normal distribution is a different kind of random variable. It's continuous rather than discrete. So let's contrast that with the four-coin experiment. All right, so in that case, you toss 4 coins, you see how many heads you get. So we have a probability axis. And if you go back to your coins list, we've actually studied this thoroughly. The probability of 0 heads is 1 over 16. 1 head is 4 over 16. 2 is 6 over 16. 3 heads, 4 over 16, 4, 1 over 16 again. Here the mean is 1. You remember it's, no, 2 rather. It's 4 over 2, which is 2, and the standard deviation is 1. 4 over 4 is 1. Okay, but the most important distinction is the only values that this random variable can take on are 0 through 4, the counting numbers, 0, 1, 2, 3, 4. If you toss 4 coins and see how many heads there are, you can't get 3.5 heads or 2 1/3 heads. It has to be an integer, a counting number. So there are gaps between these red lines. By contrast, for any normal distribution, the random variable can take on any value. Furthermore, when we look at a probability graph such as this for a discrete variable that can just take on fixed number of values, probability corresponds to length of these lines. But in this context, probability has nothing directly to do with length, it has to do with area. So if we want to find the probability that z falls between -1 and 1, we have to figure out what this area is. And we learned how to do that last time. So I hope you have your exercise set 9. We're going to look at we're going to look at modeling using normal distributions. So in the real world, certain quantities occur in populations that we can model with normal distributions. And the example I want to discuss is, I don't know if we'll get to 2 examples, I'll try, but I'm going to try to keep it down to about 15 or 20 minutes maximum. Okay, so my example is it's taken from another textbook. Let's consider the population of college-age women and consider their height in inches. So x equals height in inches of college-age women. So this can be modeled. In other words, it's approximately a normal distribution. So we can model with a normal distribution. I'm going to use the acronym ND for normal distribution. With mean 64.5. So that's 5 feet 4.5 inches, and standard deviation 2.5. Okay, so the standard normal distribution had mean 0 and standard deviation 1. This one has this mean and this standard deviation. All right, so now we can do some interesting calculations using this model. So let's begin by, I want to draw a sketch of this normal distribution. Okay, so the mean here is 64.5. I'll remind you of that. The mean is 64.5. The standard deviation is 2.5. All right, so we're here, and then we go to the, we go from left to right, and we have concave up and then concave down and concave up again. So here are 2 points of inflection. So 64.5 plus 2.5 plus the standard deviation is 67. And 64.5 minus 2.5 is 62. Okay, so this probability distribution models height of college-age women in inches. Now this is the mean. This is the mean plus a standard deviation. This is the mean minus a standard deviation. Okay, now for the Standard normal distribution, the mean is 0 and the standard deviation is 1. And if we back away, we would be at -1. Now, in all of these problems in parts B and C of your exercise set, you have to have a way of converting these values to these values. All right, how do you do that? So the value down here, the z value, is the number of steps that you have to walk in order to go from the mean to the value that you're given. So to go from 64.5 to 67, you have one stride of length 2.5. To go an additional step, which would take you to 69.5, that would be 2 steps. So this x value, these x values, 62, etc., correspond to these z values. 62, 64, 67, 60, correspond to these z values. How do you convert from one to the other? Well, it's quite easy to do that. I'll put the formula here. Converting from x values to z values. Whoops. All right, z is x minus mu over sigma. It's as simple as that. So let's do one example. So for 69.5, z would be 69.5 minus 64.5 over 2.5. So that's 5 over 2.5. It gives us the value 2. All right, let's look at a couple of problems now.